Okay, again, if you're having to watch this from home, we're looking at what waves can do that particles can't. So waves can diffract. That means they can sort of bend around an obstacle. I'm going to show you a quick little ripple tank here as a simulation. And then the application we'll look at is speakers. And I have a setup here so you guys can see how that, or hear how that works. So here's a ripple tank. Ripple tank is a way of visualizing water waves. And maybe Luca can grab the lights for me. This point up here is what's called like a point source, and it's producing circular waves. I can change that from a point source to I thought I had I'm not sure where the other one is. Let me show you what this would look like if it were diffraction. This is not the best one. Let me do the, oh, there's plane waves. This is what I wanted to show you. This would be when I had you guys walking out in the hallway the other day. You were sort of like soldiers walking arm in arm, and so the black portion could be like a crest, the bluish portion a trough, and so forth. If I increase the source frequency, what happened to the wavelength? If I make the frequency higher, should make the wavelength shorter, and so you can see that for something like that, a higher frequency produces a shorter wavelength. Now, I'm going to clear those waves, and I want to look at this thing called diffraction. So I'm going to look at a half plane. Now I'm going to bring this thing down here, redo these waves. I'm going to slow this down a little bit, and I'm going to increase or decrease that frequency a little bit. So let me clear those waves. As that's coming in here, that barrier that exists there is going to block those waves, except you'll notice that on the downstream side of that, the waves sort of turn in almost like into circular waves there. So plane waves are turning into sort of like a circular wave. If I'm on this side of that barrier, I'm going to feel a smaller amplitude, but I'll still feel some oscillation there. I'm going to go to a 3D view so you can see that better. So let me clear those waves, and you can sort of watch that coming in here. So those could be water waves, and there's some barrier there. And that barrier, again, is going to block those water waves, but it will diffract. And so the circular portions that you see on the downstream side is what we call diffraction. Okay, so waves are able to do that. Now, there's lots of different things I could do with that ripple tank as a simulator, but diffraction, it probably has its most important application related to speakers. So the idea behind this, if you have a subwoofer in your car or in your home, subwoofers are very good for producing low frequency sounds. And the reason for that is that the size of the wavelength, the closer it is to the size of the speaker, if I'm producing a sound wave that has a wavelength that matches the size of that speaker cone, it spreads out really well. The diffraction is wavelength dependent. The closer the speaker is to the size of the wavelength that it's producing, the more that wave spreads out. Now, there's various sizes of speakers that you would use in a standard like home stereo system. Your subwoofer is good for bass. Your tweeter is more for the voice and for the higher frequency sounds from maybe other kinds of instruments. And then super tweeter is designed for very high frequency sounds. This is what gives things sort of like a little bit of like shrill to a particular sound. Is the high frequencies. This is more of your bass, right? And so ideally, a really good stereo system is going to have all four of these speakers so that it produces sound that really spreads out. Now, what I'd like to do is a quick little demonstration around this table. Sound does travel, but it works better if you're close. So if you would just come around just the table, I'm going to play this little speaker here for you. Now, if you're listening to this at home, you're going to hear some sounds that are being created, but you won't be able to see the actual thing here. So this little speaker is hooked up to this function generator, and what I want to do is I just want to play a variety of different sounds. First, this is a 12 centimeter speaker. If I were to take, could you hear me? Sorry. If I were to take, if I want to determine the wavelength, that would be 12 centimeters. Let's see, the wavelength, if I play a 12 centimeter wavelength sound wave, that speaker should spread that wave out really well because that matches the size of that speaker. So what would be 12 centimeters? You can see frequency is velocity over wavelength. So the speed of sound 340, if that's a 12 centimeter speaker, or yeah, 12 centimeter long. I'm going to divide that by 0.12 to put it in meters, and that's about 2833 hertz. So if I were to play a 2833 hertz sound wave, that speaker would spread that sound out really well. I'm going to start with 100. Now this is a sine wave, so it's going to be monotone. As I play that speaker is producing about 100 hertz of sound. That speaker cone is vibrating. Again, you just touch that cone, you can feel that it's vibrating about 100 cycles per second. We can hear that. This is about as low of a frequency that we're supposed to be able to hear, about 20 hertz. Now, probably what you're hearing is just some distortion inside there, so that speaker is vibrating about 20 cycles per second. So you guys can hear it, yes? Okay. That speaker doesn't produce that sound really well because the wavelength of a 20 hertz sound wave, 340 meters per second, divide that by 20 hertz, that wavelength is about 17 meters. So that is far too small of a speaker to produce a 20 hertz sound wave and have it spread. So it doesn't work really well. If you put your ear right over top of that, it's going to give you a pretty good sound, but it doesn't spread a whole lot. Now what I'm going to do is I'm going to put this thing at, what did you say it was, 2833? That's the ideal frequency for that particular speaker. So let's put that first at 1,000 and just see if you guys can hear that. Sorry, I'm going to take the volume down a little bit so we don't have people out there thinking it's a fire alarm drill. That's 1,000 hertz at 1 volt. Can you guys hear it? Now, the speaker produces that sound pretty well, but it doesn't diffract really well, meaning that where Abby is, that sound is somewhat directional. It'll go this way, but it doesn't spread out really well because it's not a great match. So you can hear it, but it's probably not as good as if you're here right in line with that. Just to test that, what I'm going to do is I'm going to point this thing sort of at Amelia. That sound is somewhat directional. Can you hear it okay? Now what I'm going to do is I'm going to point this thing this way. I'm going to point this thing this way, and what should happen is that you should hear it less well, and you should hear it better as I start to direct it more towards you. It doesn't spread out that well towards you. Now you can still hear it, but it doesn't spread as much. Now what I'm going to do is I'm going to play 2833. 2833. This is exactly the frequency that thing is designed to make. That's as quiet as I can make it.
You don't need to point at me again.
Now, when I point at you, you can still hear it pretty well. The idea here is that as I move this thing around, it spreads out really well. You can still hear it pretty well. You can still hear it. So diffraction is about spreading of wave. Spreads out. Now, what I want to do, why don't we try this? I'm going to play it at 10,000 hertz, see if you guys can hear it. Let's just try it. 10,000.
Yeah.
You guys able to hear it?
Yeah.
I can hear that too. It's not too bad. I mean, I can hear it. I can't hear certain frequencies, but after I can hear 10,000. Now, this should not spread that sound out very well. If I direct this thing towards Amelia, you should be able to hear this better when it's directed towards you. Say yes or no. As I spread this thing around, can you guys hear it better when it's pointed at you? That's because it's not diffracting a whole lot. Okay, it's not diffracting a whole lot. Diffraction again is sort of like a spreading of it. Let's take it to 12,000. You guys ready? 12,000. Can you hear it? Okay, let's take it to 14.
Okay, so looks like we got a 6.
Can you hear it or no?
Yes.
If you can hear it, then you can tell when to turn it off.
Yeah.
Off? Tell me when it goes on. I can hear 14. I'm going to try 15,000. Can you hear it? No, this is much lower than a dog whistle. Dog whistle sounds like 30,000. You're not going to hear that. All right, let's try 16,000. Yeah? I'm completely ignorant of this. I cannot hear this. 17,000.
question.
Can you hear it?
Wait just a second.
17,000?
Can you turn it off?
I can turn it up, I can turn it down, I can make it reverberate, I can switch it from the back to the front. I can do all those things. All right, here's 18,000. Tell me if it's on. Tell me when it's on. It's on. Tell me when it goes on. Let's try 19,000. Can you hear it? Nope. Good, put that in or not. All right. Now, can you hear 19,000?
Yes.
Yeah. I can sense it, but I can't hear it. I feel like a little bit of cotton in my ears. Anyone else feel a little cotton? Here's 20,000. This should be the upper limit of your ability to hear. Can you hear it?
I can't hear, but I can feel.
Yeah. So a lot of times we're gonna sense the sound more than hear it. All right. Can I just leave this thing on at this, or I'm just gonna leave it at 17,500. It's a pleasing sound. You guys okay? Just leave that on.
Oh, I don't know.
Okay, so let me share with you what some business owners do. Because young people like yourself, I turned it off, right? So some young people like yourselves, you just loiter, you don't spend any money at businesses and stuff like that. You just are out hanging around. And then other people like me, they have all this cash in their pocket from winning various things. You guys like drive us away. So what the business owners will sometimes do is they'll play like over their PA system, they'll play like 17 or 18,000 hertz. Because it makes you guys be like, what the heck is that noise? And then for me, I'm like, it's fine. You're just not going much. So they can do that. Pretty much. Yeah, I know. All right. Then I'm back. You guys all passed, I think. It is off, correct?
Yes.
Okay, good. You would tell me, wouldn't you?
Yeah.
The video is still on? All right. All right. I don't know if you're watching that from home, whether or not you could actually hear that or not, but we are doing some speaker tests. All right. The amount of diffraction is wavelength dependent. It depends on the size of the wave in relation to the size of the obstacle or the size of the speaker. The closer the match, the better the diffraction. So obstacles and openings that are comparable to the wavelength of, in this case, sound, will diffract more. Okay, so it spreads more. Okay. Diffraction is one of those things that waves can do that particles cannot. Refraction, waves do it, particles do not. Reflection, can waves do it?
Yeah.
Can particles do it?
Yeah.
Yeah. So particles can reflect, but they don't behave quite the same way. So there are wave-related things, and then there are particle-related things. This next one is completely a wave-related phenomenon. The picture sort of shows us, gives you a hint as what's going on here. In contrast to particles, waves can occupy the same space at the same time. They are able to sort of pass through each other without destroying themselves. So waves are able to occupy same space at the same time. When they coexist, they interfere with each other, but they don't cancel each other out completely. You guys might remember conservation of momentum. When those two cars collide, their momentum is conserved during the collision. A lot of kinetic energy lost in that collision. So the motion of those cars will be irreparably changed from that collision. If I look at the collision of waves, here I have a crest meeting a trough. So the crest coming in from the left and the trough coming in from the right, when they coexist, so the crest and the trough, when they get over top of each other, they momentarily cancel each other out. So those two things would be there. The crest and the trough have canceled each other just for a moment, and then later in time, we have the crest and trough just continue on. So they're able to coexist. They don't permanently destroy each other. Anyone have noise canceling headphones in their with them? Do you have them with you? Are they big? Are they small? Are those noise canceling? Do they work pretty well? Do you know how they work? This principle.
Yeah. When I said that, you told me I was wrong.
Well, what did you say?
I said the police cancel each other out.
Oh, what did you said that?
At the beginning of the semester.
Oh, really? Okay.
Yeah.
So what they do, if this is noise, right? If that's noise, and then you're trying to listen to music, and that music has all this stuff on it. What the noise canceling headphones does is it samples the black wave up there. It inverts it. It creates the opposite of that black wave, and that cancels that out. Now that doesn't change the blue wave, right? So you can then listen to your music without listening to the noise, right? And so I can't believe I told you it didn't work like that. But if this is destructive interference, if this is destructive, what's the other one? Yeah, that is constructive interference. So this is how waves can sort of destruct. Well, on the right, this would be more of constructive interference. So I have a crest meeting a crest. And when those things meet, we get like 2C, and then they continue on, and they don't destroy each other, right? So they just momentarily constructively interfere. Raise your hand. You've ever been surfing? Are the water waves coming from? Is it Lake Michigan, or have you been in oceans, or where do you surf? Okay, the water waves coming out from Lake Michigan. Are they always the same size? Sometimes they coalesce and become really big waves, and other times they coalesce and they become really small waves. What's the period about how long does it take for the big waves to come in?
I don't know.
I mean, it could be a couple minutes, right?
Yeah.
So the reason that happens is that the different waves coming from different sources travel at different speeds, and at some point they're going to sort of coalesce and they'll come together and they'll produce a really large wave for you, the constructive interference. And other times we get sort of that wave combining with another wave and it destructs. So you have different wave size based on constructive and destructive interference. Now, what I'd like to do is just show you this really quick with this simulation. So the FET simulator, I think I've showed this to you guys before. No end, damping, get this thing to oscillate, and you can sort of see how that wave is creating, traveling along that medium. If I lower the tension, what will happen to the speed? If I lower the tension, I'm going to put it in slow motion. So I'm going to take that tension right now, it's high, and I'm going to lower it. What will happen to the speed at which that wave travels? It's going to decrease. I can see from that equation, right? The wave velocity is equal to the square root of the tension force divided by the mass per unit length. If I make the tension smaller, it should make the speed smaller. How's that going to show up here? The wavelength should become smaller. So watch when I take this thing down to this particular thing, and you can see that now the wavelength has become smaller, which it should, because the speed has decreased. Okay, so this is showing you a simulation to see how waves are generated from oscillating objects, and you can see the circular motion stuff from that little thing there. Now, what I want to do is I want to show you these. I want to show you the reflections and the superposition, which is what we're looking at. So let me put to a fixed end here. Let me restart that. I'm going to give it a pulse under slow-mo. And so as this thing goes through there, you should see that reflection occur. Did I talk about reflection before? Let me get rid of that. Try it one more time a little bit faster. So no damping. Let's try that again. Come on, every time it does that. No damping. Slow motion. Pulse. Okay. So as that thing's going along, it inverts on the C-clamp. I'm going to send another one here right about now. You notice that when these things hit, the inversion causes those things to momentarily destruct as they go through there. Again, I can show you, like, at some point it actually just looks like it's a flat line just simply because of that destructive interference. Okay, so that's where it looks like it's momentarily paused. Now, I'm going to change this one to a loose end. Now, what you're going to see is times where it constructively interferes. So this is constructive interference. And then other times you're going to see this as a destructive interference. Okay, so waves can do this, and as they pass through each other, they don't completely destroy themselves. It's just a disturbance of a propagation. It's just a propagation of disturbance, so they don't completely cancel each other out permanently. So waves can coexist at the same time. All right. Particles cannot do that. Particles would just destroy themselves. Now, this is called the superposition principle. So when waves coexist, they superimpose. So it's done through the superposition principle. So each wave is trying to bring, in this case, these are square waves, very common in computer systems. Each of these two waves are trying to bring that medium up different amounts. And so if I have a square wave with an amplitude of 1, and this is a square wave of an amplitude of 2, when they coexist, it's pretty simple addition, right? 2 plus 1 is just 3. And so those two waves would add to 3 just for a moment. And so that waveform would look like so. Once they pass, 2 would be on the left, 1 would be on the right, and they just go through each other. Now that would be constructive interference. This one here, I have a plus 1. What would you call the one to the right if that one's plus 1? Minus 3. So again, just like vectors add, if this were a plus 1 and this were a minus 3, when they coexist, it would be down 2. And that's how we would just sort of show the superposition just for that time. Now the third one is a little bit more complicated because it's got more than just a single up or down pulse. This one is more like a continuous wave, and this is a wave with half the amplitude and it's not continuous. So what would it look like when those two overlap? So you notice this is 4 vertical lines, this is 4 vertical lines. When they coexist in that spot, what would that waveform look like? Give that a go and see if you can visualize that one. Once you have that drawing, see if your elbow partner agrees with you. Some of you were gone Friday and you did not get this sheet if you were gone Friday. This is a little wave drawing sheet that I want us to practice on. If you were here on Friday, I told you to keep this sheet because we're going to do some more with this. So, constructive interference. Wait, there's portions that's constructive and there's portions that's destructive. What would it look like here? Let's see. This portion is in a positive region. When that coexists with that portion, would you agree that when those two portions overlap, it'd be up 3? When that's in that spot, that's at that spot, this would be up 3. Now, when I'm in this spot, let's use this with a different color. When I'm here, that portion would be here, and that would coalesce with that one. You see that that portion would be like that. And so for that moment, that's what that waveform would look like. How many people were able to get that without the color coding? All right. Now, I want, for the remainder of today, what I'm going to ask you to do, this sheet that I handed out on Friday, I asked you guys to draw twice the frequency, twice the amplitude, and then half the frequency, half the amplitude. The answers are on this side. What I want to do is I want to show you what these waveforms would look like if these two things were coexisting at the same time. What I want to do is I want to draw this one for you. So if I had on a wave or on a rope, I had something that had that amplitude and that frequency, and then I had something that was twice the amplitude and half the frequency. If these things coexisted, I'm going to show you what that waveform would look like when they coexist. 0 and 0 add to 0. So I'm just going to put a dot there to say that if each of those two waves are trying to bring up that medium with no amplitude, then 0 plus 0 is 0. I'm going to go over to this spot. When this is at its peak, this one is at 7 units up from that. So 5 plus 7 is 12. I'm going to go up here. 1, 2, 3, 4, 5. And these two waves would be at that particular spot because they add arithmetically. Now, I notice that both of these are going up, so I don't have to draw all of these things. I don't have to look at that point, this point here. I just know it's going to sort of smoothly go from here to there. Now, excuse me. When this one's at its peak, I notice that this one is at its equilibrium position. So the wave is going to have to go through that point because that's at 10, this is at 0, 10 plus 0 is 10. So I know that the waves are going to be there. Let's look in between here. I don't know exactly how it goes between these things, so I'm just going to pick a few of these points here. When this one's at 3, this one's at 9, 3 plus 9 is 12, And I would see it's somewhere around here. Sorry, that should be up closer to there. And then it looks like this one here, it looks like it sort of peaks right around there. And then it's going to sort of go like this. And again, it's just an approximation without doing each one of those points, but I can get a sense that it's looking like so. Let's go over here. Would you guys agree that's going to end here? 0 plus 0 has to be 0. Let's go ahead and pick some of these middle points here. This one's down 5. This one's up. It looks like this one's up about 7. So down 5, up 7 is about up 2. Let's see, this one is down 3. I'm going to come up here and go down 3, so there'll be 1, 2, 3. It looks like that waveform is doing one of these. Down 3, up 3, it looks like it's going right through there. What I've got here is enough points to be able to sort of draw this, that this waveform, if I were to superimpose those, that wave would sort of look like that. That would be the superposition of a half frequency, twice the amplitude, with one that's just regular frequency, regular amplitude. You'd get that blue line. If we have a chance to be able to look at musical notes through an oscilloscope, which shows you how the waveforms actually look, you would start to see some pretty complex waveforms. I don't know if we'll have a chance to do that or not. If you play a musical instrument, oftentimes I'll ask people to bring in an instrument. We'll get a microphone out and we'll look at what those waveforms look like. So if we get a chance to do that, that's more in our sound unit, which is chapter 12. Now, I did this one with you. Any questions on how I did it? I'm going to ask you to try the other 5. Now, this can be a little bit time consuming. That one there has a lot of undulations in the new wave that we drew. This one's going to take a little bit more time. This one's going to take a little bit more time. But if you just go through, you notice I picked out 1, 2, 3, 4, 5. I picked through like 6 or 7 different locations to get a sense of that wave. You can do the same thing here. Pick out 6 or 7 of those. Give those a shot. I want to see those best you can before you leave today. I'd like to see if you're able to superimpose those. So give those a go. See what you can do with those. And then for tonight, I just have 2 problems for you. Those 2 problems, again, are just on refraction. All right, I'm going to stop the video.